Section: Introduction. In this section, we discuss recent advancements in generative models that have significantly impacted various areas of artificial intelligence. In computer vision, we have seen impressive results from generative adversarial networks, diffusion models, and other techniques, particularly with models like Stable Diffusion, DAL-E2, and Imagine, which have set new standards for image quality and resolution. Additionally, video generation models such as LoRA have shown promise in creating coherent and high-quality video sequences, expanding possibilities in entertainment and media. In natural language processing, autoregressive models like GPT and Llama have demonstrated strong generation capabilities and alignment with human preferences, highlighting the potential of generative models. Inspired by these successes, recent studies have begun to explore the use of generative models in new areas, focusing on generating high-performing model parameters. These studies aim to directly create novel parameters to speed up the training process, achieving performance similar to traditional optimization methods while reducing computational costs and time. However, we recognize that previous work on parameter generation has limitations. For instance, earlier methods often generate parameters that are too small for practical use, as seen with G-point, which has only been tested on simpler datasets like MNIST and CIFAR10. Additionally, these methods struggle with conditional high-performance parameter generation, which is essential for real-world applications. While G-point allows for some control over parameter generation, it does not match the performance of networks trained through conventional methods. This leads us to our main question. Can we practically synthesize high-performance parameters conditioned on specific tasks? To improve the practicality of parameter generation, we face two main challenges. First, generating parameters for complex models requires extensive data preparation, as G-point needs to train millions of models, which is not feasible for larger models. Second, creating controllable parameter generation is difficult due to the complexity of modeling parameter distributions. To address these challenges, we focus on the conditional generation of fine-tuned LoRA, low-rank adaptation, parameters. LoRA is a parameter-efficient technique that adapts pre-trained models to specific tasks by learning low-rank matrices that adjust the model's weights. We propose a method called conditional parameter diffusion, or COND P-DIFF, which uses a standard latent diffusion model for conditional generation, creating a new set of parameters tailored to specific conditions. Our approach involves training an autoencoder on a selected set of parameters from models optimized using traditional methods, creating latent representations. We then use domain-specific conditions to train a conditional diffusion model that reconstructs these representations. During inference, the trained model generates representations from random noise based on specific task conditions, which are then processed by the autoencoder to produce new, high-performing model parameters. Our method has several key features. It shows comparable or superior performance to models trained with conventional methods across various datasets and architectures. The parameters we generate are distinct from those obtained through normal training, indicating our ability to synthesize novel parameters. And extensive evaluations demonstrate the robustness and generalizability of our approach in generating high-performance model weights. We hope our findings will shed light on the potential of applying conditional diffusion models to parameter generation and pave the way for task-specific parameter generation in neural networks. In the preliminaries, we explain that LoRA enhances the efficiency of fine-tuning large pre-trained language models by reducing the computational demands of full model retraining. LoRA introduces two trainable matrices to each transformer layer, allowing for a low-rank approximation of the updates needed for task-specific adaptation. This approach significantly reduces the number of trainable parameters while maintaining performance, as the original weight matrix remains unchanged. The modified forward pass in LoRA shows how these matrices integrate into the model, ensuring efficient training and deployment. Our goal is to synthesize LoRA parameters due to their practicality and effective fusion, which demonstrates a continuous distribution in the LoRA parameter space. Section Summary. In this section, we discuss recent advancements in generative models across AI domains, highlighting their impressive capabilities in image and video generation, as well as in natural language processing. We introduce our method, Conditional Parameter Diffusion, COND P-DIFF, which aims to synthesize high-performance parameters for specific tasks using a conditional latent diffusion model, addressing challenges in parameter generation and demonstrating superior performance compared to conventional optimization methods. Section: Preliminaries of Conditional Diffusion Models. In this section, we discuss the preliminaries of conditional diffusion models. These models enhance the standard diffusion model by integrating conditions into both the forward and reverse processes. The conditional information, denoted as C, enables us to generate data that meets specific attributes or requirements. For the conditional forward process, we add noise to an initial sample while considering C. The transition probability from one state to the next is modeled as a Gaussian distribution, where the mean is a scaled version of the previous state, and the noise level varies with time. The overall forward process conditioned on C is the product of these individual transitions over time. In the conditional reverse process, we aim to reconstruct the original sample from its noisiest state, again considering C. This process is defined by a Gaussian distribution where the mean and variance are determined by a neural network that also takes C into account, ensuring that the data recovery aligns with the specified conditions. For optimization and inference, we minimize the Kullback-Leibler divergence between the forward and reverse conditional distributions during training. When generating new samples, we condition on C and apply the learned reverse transitions from a noise distribution, allowing us to create data that adheres closely to the specified conditions. We propose a method for conditional parameter generation to create new parameters tailored to specific task conditions. Our COND P-DIFF framework begins with a training dataset of model parameters, from which we use an autoencoder to extract and reconstruct latent representations. We then train a conditional latent diffusion model to generate high-performance parameters based on specific task information. After training, we can generate the desired parameters by inputting random noise and task-specific conditions into the conditional parameter diffusion model. In terms of dataset preparation, we focus on synthesizing LoRA learnable matrix parameters from fine-tuned models. We fine-tune a pre-trained model using LoRA on a specific task dataset and collect various checkpoints. We denote our training dataset as a collection of weights from different fine-tuning stages. Since our dataset consists of model parameters rather than traditional image or language data, we apply task normalization through z-score normalization for each task. For the training procedure, we take a training sample, flatten the parameter matrix into a one-dimensional vector, and use an autoencoder to obtain meaningful latent representations. We introduce Gaussian noise to the latent vector to enhance the autoencoder's robustness. The autoencoder process involves encoding the parameter vector and then decoding it while adding noise. We train the autoencoder by minimizing a specific loss function. Section Summary. In this section, we describe conditional diffusion models that enhance standard diffusion processes by incorporating specific conditions to generate tailored data. We outline our approach for synthesizing model parameters using a conditional latent diffusion model, which involves training an autoencoder to extract and reconstruct latent representations of parameters, followed by generating new parameters conditioned on task-specific information. Section: Conditional Parameter Generation. In this section, we utilize a conditional latent diffusion model to create high-performance parameters based on specific conditions, such as text and images. To accommodate various tasks and modalities, we implement a domain-specific encoder, which we refer to as tau for the text domain, where the input condition is represented by y and the encoder parameters by rho. For our NLP experiments, we use the text decoder from CLIP. Inspired by in-context learning, our input condition y includes a task description and two examples to capture task details. In style transfer tasks, we use stylized images as conditions and employ ResNet to extract style representations. Regarding the U-Net architecture, we apply one-dimensional convolutions in denoising autoencoders since the weight parameters do not exhibit strong positional relationships like the two-dimensional relationships found in images. We train our conditional latent diffusion model using a specific loss function that involves the learned parameters and the conditions provided. In the experiment setup, we evaluate our method across different domains. For NLP, we test on the glue benchmark, while in computer vision, we focus on style transfer tasks using the SEM-Art and WikiArt datasets, measuring performance with the Frechet inception distance, where lower scores indicate better results. For our NLP experiments, we gather 150 training samples for models like BERT, RoBERTa, and GPT-2. For BERT, we fix pre-trained parameters and fine-tune the network using LoRA, conducting a hyperparameter search to find the best settings. We save the last 150 steps of the fine-tuning process, which includes the learnable matrix weights. In the COND P-DIFF framework, we use 1D-CNN-based encoders and decoders, with the text encoder from CLIP serving as our condition text encoder. In style transfer tasks, we fine-tune attention modules of the PixArt Alpha model using LoRA and collect the last 64 checkpoints every 10 steps. We also use pre-trained ResNet 18 to extract style representations. All experiments are conducted on a Linux server with 4 NVIDIA A100 GPUs, using Gaussian noise with a default amplitude of 0.001. Detailed training hyperparameters are provided in the appendix. For inference, in NLP tasks, we generate 20 LoRA parameters for each task using the conditional diffusion model and merge these with the pre-trained model, selecting the one with the best performance on the training dataset for validation. In style transfer tasks, we synthesize LoRA parameters by feeding the model with images of various styles and then merge these parameters with PixArt Alpha to generate images based on specific prompts, calculating the FID score for quality assessment. We establish baselines, including the original model with the best validation performance and a model soup, which averages the weights of fine-tuned models to improve accuracy. In style transfer, we also include a no LoRA baseline using the predefined PixArt Alpha model to highlight the effectiveness of LoRA fine-tuning. Our results show that COND P-DIFF can generate high-performance parameters based on task conditions. We present comparison results across the glue benchmark for different models, demonstrating that COND P-DIFF consistently performs well, effectively learning conditional parameter distributions. In style transfer tasks, we find that COND P-DIFF synthesizes style-adapted LoRA parameters to produce high-quality images, as indicated by lower FID scores. Additional visual results further illustrate the practical effectiveness of COND P-DIFF in generating high-performance model parameters based on specific conditions. Section Summary. In this section, we utilize a conditional latent diffusion model to generate high-performance parameters tailored to specific tasks and conditions, such as text and images, employing domain-specific encoders and fine-tuning techniques. Our experiments demonstrate that COND P-DIFF effectively synthesizes model parameters, achieving competitive performance across various NLP and style transfer tasks, as evidenced by evaluation metrics like the Frechet inception distance, FID. Section: Ablation Study. In this section, we conduct several ablation studies to examine the features of COND P-DIFF. We focus on the performance of generated LoRA parameters, specifically with a rank of 1, using BERT on the SST2, RTE, and MRPC datasets. Our training setup aligns with the previous experiments. We gather different checkpoints from the last steps as our training dataset for the task, and we analyze how the size of this dataset affects performance. We find that as the dataset size increases, performance improves, with a notable 4.53% enhancement in the MRPC task. Next, we investigate the impact of different normalization methods on performance. We compare no normalization, batch normalization, and task normalization, which normalizes parameters for each task individually. Our findings indicate that task normalization consistently yields the best results, while no normalization performs the worst due to the high variance in weight distributions across tasks. Batch normalization also underperforms compared to task normalization because it creates misleading correlations among parameters. We also explore how to effectively represent task conditions to guide parameter generation. We categorize our representations into 4 types: one-shot vectors, task descriptions, two-shot examples, and a combination of task descriptions with two-shot examples. Our results show that combining task descriptions with examples leads to better performance, highlighting the benefits of in-context learning. When generating LoRA parameters, we typically do so for all blocks. However, we examine the effectiveness of generating parameters for only specific blocks. Our experiments reveal that generating parameters for all blocks is more effective, as it allows for a larger exploration space, which enhances performance. In contrast, focusing on a limited set of parameters restricts this exploration. We then analyze COND P-DIFF in detail, addressing 2 key questions: whether it simply replicates training data or generates distinct high-performance parameters, and whether the generated parameter space is generalizable. We calculate the distance between generated and original parameters and observe that COND P-DIFF achieves better performance across various datasets while maintaining different similarities compared to the original weights. Using t-SNE, we analyze the distributions of generated parameters versus original fine-tuned weights. We find that the distributions differ significantly, with COND P-DIFF creating novel high-performance parameters that are more widely dispersed, indicating its ability to discover new parameter configurations beyond traditional optimization methods. Interestingly, the high-performance parameters generated for different datasets show similar distributions, emphasizing the importance of exploring this parameter space. We visualize the generation process of parameters at different time steps during inference, showing that while generated parameters approach the original ones, they ultimately remain distinct. This suggests that COND P-DIFF produces high-performance parameters that are not mere replicas of the originals, demonstrating its robustness. Finally, we assess the generalizability of the generated parameter space in image-style transfer tasks. We interpolate between parameters generated for 2 distinct styles and evaluate the effectiveness of these interpolated parameters. Our results illustrate a smooth transition in style as we adjust the interpolation factor, confirming the generalization capabilities of the generated parameter space. Section Summary. In this section, we conduct ablation studies to evaluate the performance of COND P-DIFF in generating LoRA parameters for BERT across various datasets, finding that larger training datasets and task normalization methods significantly enhance performance. We also demonstrate that the generated parameters are distinct from original ones, showcasing their generalizability and ability to explore a broader parameter space, which leads to improved outcomes in tasks like image style transfer. Section: Related work. In this section, we discuss related work on diffusion models, which have recently become a strong type of generative model, allowing us to create complex data distributions with high quality. We can categorize the research on diffusion models into 4 main areas. First, some studies aim to improve the quality of image synthesis. Second, others focus on speeding up the sampling process. Third, there is a growing interest in re-evaluating diffusion models using continuous analysis methods, like score-based generative modeling. Lastly, the success of diffusion models has led to their application in various fields. We specifically explore conditional diffusion models in the context of generating parameters. Conditional generation has gained traction in both computer vision and natural language processing, leading to 3 key frameworks: conditional GANs, conditional VAEs, and conditional diffusion models. These frameworks use conditions to guide the generation process, resulting in data samples that are both visually coherent and semantically meaningful. Conditional GANs generate images based on specific attributes or labels, while conditional diffusion models improve upon this by creating images from textual descriptions, achieving better synthesis quality than GANs. Building on the success of conditional diffusion models, we aim to extend this method to generate neural network parameters based on specific conditions. In recent years, the field of parameter generation has advanced significantly, with approaches like hypernetworks and generative models for neural network checkpoints showing promise. Hypernetworks learn parameters for one neural network using another network, while model-agnostic meta-learning focuses on efficient fine-tuning. Other methods predict parameter updates based on initial inputs and prompted errors, and some leverage autoencoders to sample new model weights. We differentiate our work by concentrating on conditional parameter generation to produce high-performing weights tailored to specific task conditions.